In this problem, we're going to draw a free body force diagram for a block that's on a ramp. We'll also find the components Fgx and Fgy. From those, we'll determine the tension force and the normal force acting on this block. First, I'll represent the block as a particle. And I want to think about what forces are acting on it. So there's going to be a gravitational force pulling directly down. However, for right now, I'm going to represent that as a dashed vector. The reason that I'm doing that is because I want to split my vector up into two components, an x component and a y component. The x direction will be down the ramp, and the y direction will be perpendicular to the surface of the ramp. So let's go ahead and draw those components, and those I'll draw as solid vectors now. And once again, the reason why I draw the original vector in dashes and the components in solid form is that I don't want to convey to a reader that there are three separate forces here. It's really only just one gravitational force, which has been broken up into components, Fgx and Fgy. Okay. We want the lengths of our forces to represent their relative magnitudes. So from this, I can determine how big the tension force should be. We need to have equilibrium because our block is at rest. And in order to achieve equilibrium, the tension force has to be just as big as that Fgx, but in the opposite direction. Similarly, in order to achieve equilibrium, we need our normal force to be just as large as the Fgy here, but it needs to be in the opposite direction. So it looks like these four are balanced now, and that's what we need. Now let's find the components Fgx and Fgy using their formulas. The formula for Fgx is going to be Fg sine of the theta of the ramp. Now notice, it's not the theta of the Fg vector itself. Like, it's not a standard position angle that we're talking about here. That's why we're using sine with x, because it's a totally different angle. It's actually the ramp angle. Our theta of the ramp is 30 degrees. Now, we can turn this into a vector if we want, and we would add an I hat on the end of it. I hat points in the positive x direction. All right, so what is our Fgx? We're going to need to find Fg first. So it's a 20 kilogram box. So according to the formula, m times g let's multiply the mass of the box times 9.8 newtons per kilogram. (196 newtons). So that's going to be our Fg in the formula here. Okay, we'll do a sine of the 30 degrees and then put an I hat on it. It's 98 newtons pulling down the ramp surface. Alright, so now let's try FGY. FGY has the formula FG cosine of theta ramp. Now if we're to plug those things in, let's see what value we get. $170 newtons. Now, if we want to turn this into a vector, we do have to look at the picture and decide whether we should put a negative on it or not. So, FGY as a vector here would not actually be 170 newtons j hat, because that would be in the off-ramp direction. It would be in the positive y direction. So we have to be able to look at the picture and know that we need to assign a negative to this. Because our FGY points into the ramp surface in the negative y direction. Okay, so can we finally answer the last two questions? What's the value of the tension force and the normal force? Well, in order to achieve balance with the FGX, which is 98 newtons, our force of tension also has to be 98 newtons. But just keep in mind that this one would be in the positive I direction and this one would be in the negative I direction. When it comes to the FGY, we had seen that FGY would be negative 170 newtons in the J direction. So Fn must be 170 newtons in the positive J direction. Now we have equilibrium.